The 5G cellular specification mandates that the network must support up to 1 million individual devices per square kilometer. That density translates directly to billions of active concurrent mobile connections fighting for routing space at any given second. This physical scale exceeds the operational limits of the IPv4 architecture, which was codified in 1981 under RFC 791. For decades, the industry narrative has focused heavily on address exhaustion. The assumption is that we needed the 340 undecillion unique IP addresses provided by a 128-bit space. But focusing strictly on the address pool masks the real engineering achievement. The primary design goal of RFC 8200 was computational efficiency, stripping processing burdens out of the network core. To understand the modern internet, we have to look past the 128-bit address space. The logic governing how packets move was rebuilt for hardware-level speed. The legacy IPv4 header is a variable structure. Depending on which optional fields are included, it ranges anywhere from 20 to 60 bytes. Because of this variability, every router along a packet's path has to burn CPU cycles reading the header length field just to calculate the exact mathematical offset where the data payload begins. IPv6 standardizes this geometry. The header is permanently fixed at 40 bytes. The payload always begins at the exact same offset. The IPv4 header also contained a checksum. Because the time-to-live field decreased to every single hop, routers had to pause and recalculate that checksum constantly. RFC 8200 removes the header checksum completely. Error checking is offloaded entirely to the network edges, handled by lower-layer protocols like Ethernet and upper-layer protocols like TCP. Optional data is now handled through a modular system called extension headers. These extension headers are placed between the base IPv6 header and the transport layer. Intermediate routers bypass them entirely unless a packet specifically flags them for processing. Standardizing the header geometry removes software processing from the forwarding path. It allows hardware-based packet processors, like ASICs, to route traffic predictably with minimal latency. Scaling this architecture down to the local network reveals a different bottleneck. Assigning individual IP addresses to billions of autonomous devices requires intense overhead if managed by centralized DHCP servers. Stateless Address Auto Configuration, or SLAAC, resolves this. A device assembles its own 128-bit address autonomously. When a host initializes, it uses a local FE80 prefix to generate a link local address. It then sends an IPv6 neighbor solicitation to the network. This verifies the IP is unique, a process called duplicate address detection. Once cleared, the host sends a router solicitation. The local gateway replies with the global prefix for that specific network, and the host appends its own identifier to form a complete routable address. Early IPv6 implementations generated that interface identifier using the modified EUI64 format. This method embedded the device's permanent hardware MAC address directly into the IP. Because the MAC remains constant, a device broadcasts its hardware identity across every global network it joined, allowing third parties to track user movements. Modern operating systems use privacy extensions, codified in RFC 8981. The trailing 64 bits of the address are automatically randomized at regular intervals. Combining SLAAC with privacy extensions yields a network where endpoints provision their own secure connectivity, independent of centralized server management. Local connectivity in IPv4 relied on the Address Resolution Protocol, or ARP, to map IP addresses to physical MAC addresses. ARP operates via broadcast. A single query acts as a hardware interrupt, forcing every single device on a local network segment to wake up, process the packet, and determine if it needs to respond. In dense environments like IoT sensor grids, that constant background noise consumes processing power and reduces the available bandwidth for actual data transmission. IPv6 replaces ARP with the Neighbor Discovery Protocol. Instead of broadcasting, NDP uses a solicited node multicast address. A router derives a specific multicast group based on the last 24 bits of the target IP. When it sends a query, only the intended node receives it. Replacing broadcast traffic with strict multicast guarantees silent local segments. Network capacity remains stable regardless of physical device density. The transition to IPv6 requires abandoning the belief that network address translation is a required security protocol. NAT was engineered strictly to conserve IP addresses. By hiding multiple private addresses behind one public IP, it breaks the Internet's original end-to-end design and complicates encrypted protocols like IPsec. To function, a NAT gateway must track the state of every active connection in a massive translation table. This creates a hard throughput bottleneck and a target for denial of service attacks. IPv6 restores the end-to-end routing model. Every device has a globally routable address. Perimeter protection is enforced directly through stateful firewalls instead of translation tables. Large mobile network operators have aggressively adopted this model, migrating to IPv6-only core networks to eliminate the latency and infrastructure costs of carrier-grade NAT. To ensure modern smartphones can still reach legacy IPv4 servers, carriers use a transition architecture called 464 XLAT. A software component on the handset, the CLAT, translates outbound IPv4 application packets into IPv6. The data travels over the cellular network natively. At the carrier's edge, a provider-side translator strips the wrapper. The packet reverts to standard IPv4 before entering the legacy internet. Native routing paired with 464 XLAT allows operators to preserve their dwindling IPv4 address pools while running a state-free mobile core. Operating these networks requires engineers to adapt their standard diagnostic tools to handle strict address scoping. Attempting to run a standard ping on an IPv6 link local address will immediately return an invalid argument error. Because the link local prefix exists on every physical network interface by default, the operating system cannot route the packet. The engineer must explicitly define the outbound interface index for the command to execute. RFC 8200 moves IP networking away from variable processing and central address tracking. It establishes a highly predictable, decentralized architecture. Deploying massive high-density infrastructure, like smart city grids and autonomous vehicle networks, demands this level of structural precision. Adopting IPv6 solves the address shortage, but its primary function is providing the core engineering substrate required to sustain the future of global telecommunications.